Hey, physics, welcome to another flipped lecture. I can say that 2 times fast. Last time you got to see me on my front porch. Now here I am in my living room on my couch, and welcome to my home. And I hope that we're going to have a good time here talking about thermal expansion. So chapter 14, like chapter 13, is largely reviewed. There's a ton of stuff in here you've already seen. 13a gives a little bit more reason. Sorry, 14a gives a little bit more reason for why things expand when they get bigger than you've seen before, but you already know that that's true. We're just going to do a little bit of math with that to demonstrate how they get bigger and to what degree they get bigger and things of that nature. Okay, so we're going to jump right into it here. Thermal expansion, as substances heat up, their particles have more kinetic energy. And so the increased kinetic energy causes them to vibrate faster if they're a solid, or to move faster if they're a liquid or a gas. And that increased thermal energy, increased movement at the molecular level, causes the substance to expand. And so the expansion is proportional in all directions, meaning that the substance will get as much taller as it does deeper or wider, proportionally to the thickness that's already there. Your book makes a big deal about the fact that it's proportional in all dimensions. So if you have a wire, for example, a copper wire that is 8 feet long, but only 1/8 of an inch thick, it's going to get a whole lot longer than it gets thicker when it gets hot, because it's proportional. There's only 1/8 of an inch of copper. It's only going to get just fractionally bigger. But if there's 8 feet of copper going in this dimension, then when that expands, it's going to be a lot longer. So that is an important thing to keep in mind. Expansion is proportional, and it is universal in the object, as long as the object conducts heat well enough to heat up at a uniform rate throughout the body of the object. Okay? Some examples of that. These are a series of whoops images for railroads. So if you are building a railroad, remember these problems, that you don't want to set the rails right up against each other, because when those rails get hot and expand, there's nowhere for them to go, and they wind up warping. You get all these fun railroad tracks that the trains can't drive down. So I'm sure all of these are examples of an engineer not having the job the next day. So thermal expansion is something that engineers have to account for and remember that they are present. Here are some other examples of thermal expansion. Here we have a expansion joint in a highway, and I'll show you why that's important in a moment. So there's lots of metal and concrete and things like that over here, and the same thing over here. And you might think that the bridges in highway overpasses are all one piece, but they're not. They're actually multiple pieces that have been joined together. And so this is a good example of one of those seams, so that the bridge doesn't move from side to side. These teeth hold that in place, but they are not, in fact, one intact unit. Boy, I'm just skipping things all over the place here. Alrighty, there we are. Heat also causes the balloons in the other picture here to expand because of heat. And so the air expands, and the air inside the balloon becomes less dense, and that's what causes them to rise. So we have lots of examples of things getting bigger when they get hot. And that exists in all 3 states of matter. The equation here, you have that the change in length, delta L, little cursive L again, delta L is equal to a proportionality constant, A, times the initial length times the change in temperature. So we use alpha there. It's the Greek letter alpha, not just the regular lowercase a. Alpha is a thermal expansion coefficient that's unique to the material. So concrete has its own value for alpha, water has a value for alpha, oxygen gas has a value for alpha, yada, 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 okay? And so the initial length is just multiplied by that expansion coefficient times the change in temperature gives you the change in length. Now, not the new absolute length, but the change in length. Ready? And you can use this for all dimensions of a regular solid. And so you can use this to, again, look at the copper wire. And if you figured out that it was going to get 5% bigger, well, however thick the copper is, times 5% more. However long the copper is, times 5% more, etc. Okay? It can be used for all those different dimensions. Here's an example of how this comes into play. So here we have a concrete overpass. Given that alpha for concrete is 9.8 times 10 to the negative 6, And the unit for alpha is inverse degrees centigrade, and that just is there to cancel out the degree centigrade and the change in temperature, so don't stress about that. It just makes the degree centigrade and the other one go away. 9.8 times 10 to the negative 6th is your value for alpha. How much room do engineers need to leave at expansion joints if they occur every 30.0 meters on an overpass, where the highest summer temperatures are 35 degrees centigrade higher than the median temperatures? This would be a massive temperature swing. Nowhere on the planet has a change from median temperature to highest recorded temperature, 35°C. But for the sake of the problem, I took a big number. Okay? So change in length equals alpha times the initial length times degrees times the change in degrees. Okay? And I just plug all my numbers in. Here's my alpha. And notice it is in inverse degrees centigrade. And then my change in temperature is 35 degrees. And the length of the concrete is 30.0 meters. Just for the sake of simplicity and showing you that the units cancel, I'm going to multiply the first times the last first. And you'll see that C negative 1 and C cancel out. Okay? So I wind up with just this number, 3.43 times 10 to the negative 4th, which is the product of these two numbers here. And then times my 30 that I had before gives me a change in length of 0.01029 meters. Significant figures, as I skim my problem up there, I had 2 significant digits in 2 of the things that were given to me. 2 significant digits is my answer, 0.010 meters, or about 1 centimeter. So that huge 30-meter bridge, or segment of a bridge, will only get bigger by 1 centimeter when the ridiculously hot days come. Okay, that's why those expansion joints don't have a whole lot of room, because they don't need to. It doesn't get bigger by feet, right? It gets bigger by centimeters, or even not even that. So the value for alpha controls that equation. You have seen that example now. Okay, just like one dimension gets bigger, if you have a solid object, or a liquid or a gas, the volume is going to get bigger as well when it gets hotter, and it's the same kind of equation, right? Instead of change in length, now we have change in volume. And we have, just like we had alpha before, which was my linear expansion coefficient, now they use beta, and it's our volume expansion coefficient, okay? And just like alpha, it's unique to every material. You need to look up what the beta value is for that material if you're doing work like this. And then it's just beta times the initial volume times the change in temperature, okay? Volume sub I is the initial volume there, and then we use the this same equation for liquids and gases and solids. It doesn't matter what state of matter it is. Really, a liquid or a gas doesn't have a linear measurement, so you can't use the first one, but you can use the second one for liquids and gases. So let's look at an example of that. Here we have Lake Superior, one of the largest bodies of water on Earth, one of the largest freshwater bodies of water on Earth. In spring, Lake Superior has a volume of 12,100 cubic kilometers. That's a lot of water. A cubic kilometer is 1,000 meters by 1,000 meters by 1,000 meters. That's really far. And this lake has 12,100 of those of water. That's a lot of water. So the median temperature of the water in April, and I looked this up, is 4 degrees Celsius. Okay, just above freezing. It actually freezes. The temperature of the lake will drop down to 0, and colder, actually, in the winter. But we're in April, right around when it's thawing and melting. We have a median lake temperature of 4 degrees Celsius, just above freezing. In August, so the hottest part of the year, it doesn't actually get all that much hotter. The median temperature is still cold, but it's risen to 7 degrees Celsius. So how much bigger is the lake in August than in April? And of course, we're making a faulty assumption here. We're assuming that none of the water leaves the lake and no new water flows into the lake. In truth, the lake is always being filled and drained. But let's just pretend that we don't know that. And let's say we have this 12,100 cubic kilometer volume of water at 4 degrees, and we heat it up to 7 degrees. How much larger is the same amount of water at that temperature? So change in volume is beta times the initial volume times the change in temperature. Beta for pure water is 2.07 times 10 to the negative fourth degrees Celsius inverted, or the reciprocal of degrees Celsius. So we have that number to plug in. So I'm going to put beta in here. This is my initial volume, just turned into a more usable scientific notation kind of number. And my change in degrees is only 3 degrees Celsius, from 4 degrees Celsius to 7. All right? So I'm going to multiply, just like I did before, the degrees Celsius times the beta, so I can cancel the units and show you that they cancel out. So 2.07 times 10 to the negative fourth times 3 is 6.21 times 10 to the negative fourth, and the degrees Celsius and the degrees Celsius negative 1 canceled out. And now I have my volume, 1.21 times 10 to the fourth cubic kilometers. Multiply those two together, and the lake got bigger by 5.5141 cubic kilometers. Correcting for significant digits, it got bigger by 5.5 cubic kilometers. That's a whole lot more water volume. Now, in truth, Lake Superior drains here into a river and eventually goes into the other Great Lakes. So where does that additional 5.5 cubic kilometers of water go? Well, down the river into the next lake. So the lake doesn't actually sit higher on its shore because it'll just spill out the bottom here. But again, in a simple idealized world, that's a lot bigger lake than what it was in the spring. Alrighty, and I think that actually does it for me. Yes, it does. Let me know if you have any questions. Post any comments or questions in the comments field below, and I'll see you in class tomorrow. God bless you.